So, last lecture I introduced binary quadratic form, I defined its discriminant and I told you what the action of SL2Z on the set of binary quadratic forms is. And we also proved that the action keeps the discriminant same. So, that defines an equivalence on the set of binary quadratic forms, and not just the set of binary quadratic forms, but also binary quadratic forms of a given discriminant, and we want to understand this. So let us recall all these things again. So, a binary quadratic form is an expression of the form ax squared plus bxy plus cy squared. Okay, that is what a binary quadratic form is, and we will often denote it as a comma b comma c, and p q r s acts on this by the following. So, you take b by 2 and c here, and then p q r s transpose. So, this gives an action of SL2Z on SD, which is A B C such that b squared minus 4 AC is equal to D. So, this is the discriminant that we saw last time. Okay. And our aim, our goal today is to find when D is less than 0, want to understand equivalence classes. So, SD modulo SL2Z. Okay. So, this is equivalence classes. Okay. So, this is not I am not saying that SL2Z is a subgroup of SD, I am just saying that there is an action of SL2Z on SD, and this is what I denote the equivalence classes by. Okay. So, recall that A, B, C is called positive definite, if b square minus 4 AC, this is the discriminant, is less than 0. Okay. Because we can, in this case we can assume that A is positive, and we can then the quadratic form only represents positive integers, okay, except when x equal to y equal to 0. Okay. So, here is a theorem that we want to prove today. Okay, before that let me give a definition. A positive definite binary quadratic form A, B, C is called reduced. So, that is what I am defining. If A is bigger than 0, so that is one condition. 2, mod B is less than or equal to A, less than or equal to C, and 3, if mod B is equal to A or A is equal to C, then B is bigger than or equal to 0. Okay. So, that is what a reduced binary quadratic form is. Okay. So, example, if I take something like 1 0 1, then this is a reduced binary quadratic form. Binary quadratic form of discriminant minus 4. Okay. or I could take 2 1 1 sorry 2 1 2. So, this is also a reduced binary quadratic form of discriminant minus 15, or I could take 2 minus 1 2. This is not a reduced binary quadratic form. Okay. Its discriminant is also minus 15, but this is not a reduced binary quadratic form. Okay, fine. So, what is the theorem? The theorem is the following. There is exactly one reduced binary quadratic form in each equivalence class, of positive definite binary quadratic forms. Okay. So, we need to prove two things. Okay. So, we need to prove two things. We have to prove one, any positive definite binary quadratic form is equivalent to a reduced one, and two, no two reduced binary quadratic forms are equivalent. So, if A, B, C and A prime, B prime, C prime are both reduced and A, B, C is equivalent to A prime, B prime, C prime, then A is equal to A prime, B is equal to B prime and C is equal to C prime. Okay. So, these are the two things we need to prove in order to prove the theorem. So, let us take the first one. So, let A, B, C be a positive definite binary quadratic form. Okay. We want to show that there is a reduced binary quadratic form that is equivalent to this one. Okay. All right. So, how do we do that? Well, first of all, we can assume that A and C are both positive. Let me just say that if A is bigger than or equal to C, then we change it as follows. So, then we let 0, minus 1, 1, 0 act on A, B, C. So, what do we get? Let us do this slowly. So, this is minus 1, 1, 0, A, B by 2, B by 2, C, and then 0, 1, minus 1, 0, that is the transpose. And so, if you multiply this out, you get B minus B by 2 minus C, A, B by 2, 0, 1, minus 1, 0, and if you rewrite this, this will be C minus B by 2 minus B by 2 and A. Okay. So, what have we shown? So, hence A, B, C is equivalent to C minus B and A. Okay. So, we can always assume, A is less than or equal to C, otherwise you can just swap A and C and change the sign of B to minus B, right. Okay. Okay. Now, there is another nice matrix in SL2Z. So, you take 1 K 0 1, this also is in SL2Z. So, if we let this act on ABC, what do we get? 1 K 0 1 A B by 2 B by 2 C 1 K 0 1. So, if you multiply this out, you get K B by 2 C K B by 2 and sorry, I made a mistake here. This should be A plus this, and the other one should be C K plus B by 2 and this, and then we have 1 0 K 1, right. Okay. So, if I multiply this out again, I get A plus KB plus CK squared, right. Then CK plus B by 2 and again CK plus B by 2 and C. Okay, I'm a bit worried now how, okay. Fine, maybe this is not okay. So, that's not something I want. Let me try to do the other thing. So, if I let 1 0 K 1 act on A B by 2 B by 2 and C 1 K 0 1, then this is A B by 2 A K plus B by 2 C plus B K by 2 1 K 0 1. So, this will be A and then right. So, it is A K plus B by 2 and then A K plus B by 2 and then A K squared plus C plus B K. Okay. So, I do not really care what this C is, I just care that A is left invariant and then B changes to yeah. So, let me rewrite this as A and then B plus A 2 times A K by 2, B plus 2 times A K by 2 and then some C prime here. Okay. So, I have shown that A, B, C is equivalent to A, B plus 2 A K by 2 and some C prime. Okay. For some C prime, it is a fixed and specific C prime, but I do not care about its value as much. So, now by varying my K, I can always assume. So, if I take K, yeah, let me write it like this. So, take K equal to floor of a minus b by 2a, right. So, this is largest integer less than or equal to. So, this is largest integer less than or equal to a minus b by 2a. We get that b plus a 2ak by 2, this is between minus a and a. Okay. So, what we have got is a b c is equivalent to a b prime c prime with mod of b prime less than or equal to a. Okay. So, this is almost reduced, right, because we already have this. Okay. So, if you see what the expression for c prime is, it still is, yeah. So, this is, if you see what the expression for c prime is, it is c plus a k square plus b k by 2. So, if you put the value of b in this, you will realize that c prime is still bigger than a. Okay. So, this is almost reduced except when you have equality. So, if a is equal to c prime. So, yeah, let me, so rather than writing this, let me just say the following. So, now we have, oh gosh, okay. So, we have shown that any positive definite binary quadratic form is equivalent to a b c such that mod b is less than or equal to a is less than or equal to c. So, now I further want to see what happens when there are equalities. So, if a is equal to c, then and if b is less than 0, then replace, then we know that a b c is equivalent to c minus b and a, hence minus b is bigger than equal to 0, right. So, that is kind of one thing. If b is equal, if mod of b is equal to a, okay, then again a b c is equivalent to a b plus, and let us say that b is less than 0, then this will be 2 a by 2 and c. So, again this condition will tell you that, so we can take, so b plus 2a by 2 is bigger than 0. Okay. So, hence any binary quadratic form, any positive definite binary quadratic form is equivalent to a reduced one. Okay, so that is great. Yeah. Okay. So, we have done that. Now, let's show that. So, let a b c and a prime b prime c prime be reduced. We want to show, and let us say that they are equivalent, and a b c is equivalent to a prime b prime c prime, then we want A is equal to A prime, B is equal to B prime, and C is equal to C prime, right. That is what we want. Okay. So, we computed last time. So, last time we computed P Q R S, A B by 2, B by 2, C and P Q R S, right. And so, the first quantity of this was A P squared plus B P R, not okay, not quite I guess. So, B P Q plus C Q squared, right. So, that is what it was, and then something something here, I do not care. So, this means that A prime is A P squared plus B P Q plus C Q square for some P and Q. Okay. Now, but I can rewrite this as A P square 1 plus B R by A P, sorry not R, B Q, B Q by A P plus C Q square. But I can also rewrite this in a slightly different way. I can write it as A P square plus C Q square 1 plus B by C P by Q, right. So, that is another way of writing the same thing. Right. But if A is equal to A prime, if A is equal to A prime, then the only way this can happen, the only way A prime B prime by 2, so A is A prime, right. So, let me put that anyway here, and then B prime by 2, C prime can only be of the form 1 0 K 1, A B by 2, B by 2, C and then 1 K 0 1. Okay. Sorry, I took cases here. So, if this were not true, then we would just use the second we would just use the second part of this, because in one place you have Q by P and in another place you have P by Q, right. So, at least one of them has to be less than 1. So, you either end up showing that A is equal to A prime or you end up showing that C is equal to C prime, but the argument after that is very similar. So, so that is what it is. In any case, so then B prime is B plus 2AK, right. But now A is equal to A prime, right, and B prime is less, so mod of B prime is less than or equal to A prime, which is equal to A. So, the only way this can happen is when K is equal to 0. So, hence K is equal to 0 and we get B is equal to B prime. Okay. And now we use the fact that B square minus 4AC is same as B square minus 4AC prime, right. So, hence C is equal to C prime, right, as A is not equal to 0. If A is 0, then you can't have a positive, definite binary quadratic form. Okay, great. So, we have shown that A, B, C is equivalent to A prime, B prime, C prime, both reduced implies A is equal to A prime, B is equal to B prime and C is equal to C prime. So, that proves our theorem. So, what we did today was study the equivalence classes of positive definite binary quadratic form. In particular, we defined what a reduced by positive definite binary quadratic form is. It is in terms of very nice inequalities between the coefficients, and we proved that in any equivalence class there is exactly one reduced binary quadratic form. So, next time we will see how to find all equivalence classes of reduced binary quadratic forms of a given discriminant, and we will also do, if you are given a binary quadratic form, how to find one which is how to find a reduced one equivalent to that particular one. Okay. Thank you.